All right, good to go. Sorry about the delay. Our next speaker is Ionescu. He's been with REcon for more years than I can count as both a presenter and a trainer that sells out every year that I can recall. He's been here dropping some pretty amazing research every time that he's ever given a presentation, and looking forward to hearing what he has today.
Thank you. Thank you. Sorry for the delay, everyone. I guess you're a rock star when you make everyone wait for you. Officially jumped the shark. So I'm here to talk to you about what I like to call the last generic KASLR defeat. But the keywords are generic and Win32K.sys. So I don't want anyone to think that I'm saying it's all over. But we'll see what's new and what's different. So just a little bit about myself. For those of you who don't know me, started out doing Windows internals and reverse engineering almost 20 years ago. Worked on a project called ReactOS for a really, really long time, which is an open source reimplementation of the Windows operating system. It's still alive and kicking, but I do other things now. And basically spent a lot of time reversing Windows and looking at various kernel implementations, data structures, and behaviors, ended up rewriting it as C code. And kind of as part of doing that, I learned a lot about the OS and eventually started writing the Windows internal series of books with Mark Sinovich and Dave Solomon, with other co-authors now, and started doing classes around the world. This is kind of my hobby. I like to call myself not a security researcher, even though I show up here every year. I am a boring VP now of EDR strategy and chief architect, so I mostly run engineering teams and do architecture and stuff. And actually, I always like to bring up, I never worked at Microsoft. People always think that I worked there, but I used to work at Apple actually, so never was part of the Microsoft world. So I did a lot of conference speaking. Probably a bunch of you have seen me before. And what I like to talk about is usually design level flaws, design issues, flaws or interesting features in the OS that make things different, allow you to persist, inject, or just good ways that they're breaking attackers and introducing security. So this will be more of a combination of both the defensive talk in terms of what's changing and an offensive talk about a CV that was recently patched that kind of attacked some of these changes. So I'll talk a little bit about kind of the state of KASLR in Windows, where we started from and where we are today, specifically kind of at the kernel level and the various data structures that are there. And then I'll move on to talking about this component, Win32K.sys, which is the graphics stack of Windows that I'm sure if you do Windows offensive research, you've probably seen that name come up before. I'll talk a little bit about what's changed in that component in recent versions of Windows, specifically the introduction of the kernel fixed segment heap, kind of how that works and what it's similar to and different to. And then I'll talk specifically about the issue with the implementation as it was done in Redstone 4 and Redstone 5, aka the Spring Creators update, aka 1803 and 1809. So this was patched in December, so almost 6 months ago now. But I think it's an interesting case study in how very complex work can be easily messed up by a simple mistake, which is simple to fix as well. And I'll kind of wrap up with some future direction in which KASLR, at least on the Windows side, is going. So let's talk a little bit about how we got here. So kind of the story of how Windows kernel address space load randomization evolved. So before Windows Vista, there wasn't really any kernel ASLR or any ASLR whatsoever. So you're talking fixed addresses everywhere. In Windows Vista, Microsoft introduces ASLR and KASLR. But interestingly, if you look at the acronym, it doesn't say kernel address space layout randomization. It says kernel address space load randomization. So that basically tells you that they're randomizing load addresses, but they're not necessarily randomizing all the layout. So what that means is they're going after the base address of the kernel, the HAL, the drivers, and one or two data structures. Now, on 32-bit, the problem was even worse, because not only did we not have kernel address space randomization, but the regions of memory were actually fixed in Windows Vista. So outside of kernel images, everything else was fixed at predetermined locations. And even though the heap manager tried to randomize the allocations within the kernel heap is a small 100 megabyte fixed region pre-Vista. So in Vista, we have the introduction of the kernel virtual address space allocator on 32-bit, which basically now grabs address space as it needs to. So before that, if you took an x86 Windows XP machine, this was your so-called paged pool. and then this was your non-page spool, and this is where drivers loaded, and this is where your file system cache was, and this is where your stacks came from. And so even though there was some entropy within these regions, they were fixed. And since the kernel address space is only 2 gigs on x86, well, with 2 gigs, it's pretty easy to spray any of these regions and kind of figure out where things are. So what happens now with KVA on x86 is you start with a fresh blank slate, 2 gigabytes that has nothing in it. And then over time, when the page spool wants some memory, KVA comes in and grabs some pages of page spool. And then when non-page spool wants some memory, KVA comes in and grabs some pages of non-page spool. And when there's some kernel stacks needed, we go and grab some kernel stacks. So eventually the address space becomes a lot more fragmented, which does have some performance implications. But at least on 32-bit, we now have a little bit more randomness because of the KVA allocations themselves. So that's kind of the first attempt to try and make things a little bit better. But there were still a number of issues. One of the funniest issues is that even though we randomized some things, there were APIs that were unprivileged that you could just call to basically get all this information back. I think 7, 8 years ago at REcon, I gave a talk called I've got 99 problems, but a kernel pointer ain't one, where I kind of went over documented and undocumented APIs that by design were giving you kernel pointers. So they weren't leaking the pointer, it wasn't an address on the stack or the heap that was left over. These are APIs whose sole purpose was you have a kernel pointer, you have a kernel pointer, you can have a kernel pointer too. And so there was one that leaked object addresses, there was one that leaked process pointers, thread stack addresses, driver base images. And that's because at the time, KASLR was really thought of as a mitigation against a remote attacker. And if a remote attacker can already execute code on your machine, well, then in Microsoft's world, it's not your machine anymore. But now we have this more interesting world of the local remote, right? We have a remote attacker, but they're getting inside of a sandbox inside of Edge or Chrome or IE or the mail client, and then they get code execution inside of there, and then they get into the kernel by calling an API like this. And so in the world of local remotes, you probably want to start worrying about that. APIs will just give you pointers. On top of that, the Windows graphics subsystem, Win32K, has what's called a shared heap, which we'll talk about in this talk some more. And inside that shared heap, you have pointers to a bunch of kernel data structures. You also had issues where because this component came from Windows 3.1 and 16-bit, you still had some system calls where the calling convention was still returning a 16-bit narrow type, where on 64-bit, for example, this essentially leaks basically 48 bits of the kernel pointer that may have been in RAX before you basically got the bottom of what was left in AX. You had data structures like the HAL heap, which the kernel allocated a fixed address. You had indexed arrays, like the page table entry array, the working set array, the PFN database array. These are all at fixed addresses. So even for remote attackers, getting the kernel was pretty easy because you had all these fixed blobs of memory. At a harder level, you have instructions on x86 like sgdt and sidt that give you the base address of kernel data structures. So CPU itself is helping you out by telling you where things are in the kernel. And on x64, there is no KVA allocator. On x64, they basically decided, look, we have 8 terabytes of address space, and so we can make large prefix allocations. No one's going to be able to spray them because 8 terabytes is a lot. But it turns out that 8 terabytes doesn't have to be that much. And in fact, one of the problems on Windows 8 and Windows Vista and Windows 7 was that due to a bug in the first Intel AMD CPUs, the compare exchange 16-byte instruction didn't exist. And so in order to make stack lists work, Microsoft basically had to create a 44-bit address space instead of a normal 48-bit address space. So every 64-bit in the OS in the world gave you 256 terabytes of address space. Microsoft could only give you 16 because they were being nice to AMD for people who bought an Opteron on day 0. So you only had an 8 terabyte address space instead of the full 128 terabyte kernel address space. And you had all these other issues. So Vista was kind of a baby step, but KASLR was still mostly a joke for any real attacker. Windows 8.1 comes out and makes things a little bit harder. In Windows 8.1, you now need a processor that supports compare exchange 16 bytes. So you can no longer boot on a 1999 Opteron. Because of this, they remove the S-list entry limitation, and now you actually have a full 128 terabyte address space. They still don't have a kernel virtual address space allocator. The regions are still fixed, but with 128 terabytes, the entropy is a little bit bigger, the randomness of the internal allocation helps, and things are we're raising the bar a little bit. They cleaned up the return types of Win32K.sys, so we're not returning 16-bit values anymore. And they finally introduced now a function called uXzcEpxt54ybs, which now verifies if you're calling any of these APIs in NT-query system information, which actually I put over here. If you're calling any of the ones in the REcon presentation and any of the other ones they found, they're going to check if you're what's called a restricted caller. A restricted caller is basically someone that cannot access medium integrity objects that are marked for everyone. So if something says everyone has read access at medium integrity and you can't access that, then you're a restricted caller. Right? Why would you not be able to access something that is giving everyone access? Because you know what's called an app container or a Windows sandbox. Why would you not be able to access something that has medium integrity? Because you're low integrity, because you're running a protected mode IE, because you're running in Flash or in Chrome or other kinds of sandboxes. So basically, uXzcEpxt54ybs blocks app containers, so all your Metro store apps, and blocks most browsers, blocks most email clients, most Flash, PDF readers, etc., from calling those APIs. So things are getting better from the local remote point of view. Hyper-V in Windows 8.1 also introduces something called NPIP, which most people didn't notice because Hyper-V in Windows 8.1 was not something most people enabled. What NPIP does, which is a bit of a mouthful, non-privileged instruction execution prevention, is it blocks at the hypervisor level the SGDT, SLET, and SIDT instructions. It basically returns an undefined opcode, which pretends to the processor that those instructions don't actually exist. So on 8.1, by turning on Hyper-V, you were kind of protected against those instructions, but very few people did that. But still, 8.1 kind of moved the needle a little bit further. And so all of those APIs that leaked kernel pointers were fixed, but they didn't get everything. And so, for example, I found yet another API that still leaked an eProcess pointer. Now, that's not a subject of the talk, and they fixed that in 19H1, but the point is that sometimes they will still find, you may still find APIs that give you kernel pointers, and they will fix them and they'll service them, and you'll get a bug bounty. So now it's part of the process to make sure that there aren't APIs that by design give you kernel pointers as long as you're low integrity your app container. If you're admin and you get a kernel pointer, that obviously doesn't really matter. So in Windows 8.1, for example, and this was an old blog post table that I made, the entire address space was basically predefined. Right? So your system cache was FFFFB, page pool was FFFFC, system PTs were FFFFD, non-page pool was FFFFE, and so on and so forth. And the very famous PTE space here at FFF680, which repeatedly got used to bypass various security settings by touching page table entries. So within these large regions, of course, things were being kind of randomized, within the 16 terabytes. But if you could spray, if you could leak one address and guess the next, it wasn't really ideal. Still, though, with all these improvements, we're better than Vista, which isn't saying much. In Windows 10, that's when they finally introduced an anniversary update, full address space layout randomization. So now you have 14 different defined regions of memory, things like the PFN database, the file system cache, the system page tables. All of them are randomized except one, the HAL heap. So the HAL heap remained at a fixed address because it was a little bit kind of harder to get that one. In Creators Update, so in Redstone 2, they fixed that one as well. In RS3 and Fall Creators Update, they do one more change, which is they create a 15th region of memory, which is the kernel stack region, and they separate kernel stacks from memory map mappings. And that was in direct result of a talk from Jordan Rabet from Microsoft, where he had found a Hyper-V bug. And basically the issue was that instead of a guest Hyper-V virtual machine, you could cause allocations on the host that are called gpaddles. And those allocations come from the same region of memory as kernel stacks. And so you have these potentially guest-controlled data structures next to kernel stacks on the host. And so sure enough, one of the bugs has allowed him to overwrite a gpaddle and then allocate gpaddles of specific sizes. So of course, he comes in and allocates a gpaddle exactly the size of a kernel stack, allocates one right before, frees the one in the middle. This now becomes a kernel stack once the thread gets created, and then he corrupts this one, and now you're corrupting kernel stacks. So they fixed the bug that allowed the corruption, but they said, hey, as defense in depth, why don't we also make sure that we don't put kernel stacks next to potentially Hyper-V guest memory controlled data structures? So there's now this 15th region called kernel stacks to separate things away. So in the debugger, you actually have this nice little bang VM21 extension, and that actually will tell you where all these regions are. So I've got a VM set up here, so if I do bang VM21, and I'll zoom in a little bit since we're at 1080p here. Here, all the system regions, the BFN database, session space, special pool, et cetera, ultra zero hyperspace when you want to make a jump somewhere else. All of these things should be random on my machine versus someone else's machine. The 2-3 nibbles here should be different. So you got 1 in 256 to sometimes 1 in 512 locations. Not 8 or 9 bits of entropy, but still way better than hard coding a table. And great for me writing Windows internals because I don't have to keep that table up to date anymore. Now I can just say it's random. I can't tell you what it is. Bang VM21 won't display the HAL heap. That's in another data structure. You've got to go in what's called mistate.systemva space. So if I just, hopefully this will make it in the video. Information, address of mistate. So this will be in systemva, and there you've got HAL private VA start, HAL private VA size, and those are, that's the beginning and the end of the HAL heap, which also should be random within various machines. So the regions from bang VM21, and then the regions, the HAL here from mistate, improve things a lot at the kernel level. The other thing that happens is in Windows 10, Hyper-V is now enabled in significantly more scenarios, whether you're turning on Credential Guard or Device Guard or HyperGuard or HVCI or a number of features, this will turn on Hyper-V. In fact, in 20H1, the plan is to actually have it enabled by default, at least on new installs and clean hardware. So that makes NPIP a lot stronger because now on an increasing number of Windows 10 machines, SGDT and SLDT and SIDT will no longer work. Now, on top of that, Intel on their 10th generation processors, so that would be Cannon Lake processors, they now have a technology called UMIP, which is kind of funny, User Mode Instruction Prevention, which makes it sound like it prevents user mode. This is Intel's name for NPIP. So this basically blocks SGDT and SLDT and SIDT from working in Ring 3, which they should have never really been Ring 3 instructions to begin with. But if UMIP is enabled, then you can no longer do that. And in 19H1, in the latest release of Windows 10, if you have a 10th generation processor, the OS will enable UMIP, and now Intel won't let you use those instructions. So you don't need to have Hyper-V running. But of course, with Hyper-V running, you don't need a new CPU. You can have AMD, you can have ARM. So Hyper-V gives you a generic mitigation if you enable it. Otherwise, Intel now has a specific one in hardware. And of course, Linux and Mac OS can leverage the Intel one because they don't run under Hyper-V. So with all of this, we're in a much better state at kind of the kernel-based OS level. The problem is the graphics stack, or Win32K.sys. Because when you make a graphics call for the first time, you go through a kernel function called ps-convert to GUI thread. And what ps-convert to GUI thread does, it basically says, you are now talking to the graphics component for the first time. You're talking to the window manager, or you're talking to GDI. I will now promote you to getting access to it. So one of the things it does is it switches the system call table to what's called a shadow system call table, which now gives you access to the system calls, and it notifies Win32K.sys about you. It tells the graphics stack, it tells the window manager about your thread. If this is the first thread in the process, then it tells Win32K.sys about the process as well. So it both tells you, here's a new process, and here's a new thread. Because of that, Win32K.sys then gives you some gifts. Basically says, hey there, thanks for talking to me. I've got some things I want to share with you. So in your tab, which is a user mode data structure, it populates an entire structure called tag client info. And tag client info is a kernel structure. So it basically gives you kernel pointers in your tab, and as part of that, it also maps what's called the desktop heap. Then, in another field in a tab, it gives you a kernel pointer to a structure called tag thread info. So it gives you yet another kernel pointer. Hey, you have an arbitrary right. Would you like to know where to use it? Here's a cool location. In your PEP, which is then your process environment block, which is also in user space, you get a pointer to what's called the GDI shared handle table. Now, this contains the user mode session heap, and in one of your DLLs, you then get the delta to where this session heap is mapped in kernel mode. So I map you a kernel heap in user space, which is chock full of kernel pointers, and then I tell you the delta. So I basically tell you where it is in kernel space, because I tell you the difference between your mapping and where I have it. So you basically get thousands of kernel pointers, you get the deltas, and these are all gifts that you get just for doing a simple graphics call. So obviously all your browsers, all your email clients like PDF readers, almost any app in the world gets these gifts because it's impossible not to write a GUI app in Windows at the end of the day. Command line doesn't matter. Even a service is going to do at least one GUI call to do some graphical thing. So they recognize that and say, okay, well, we did all this work at the kernel level to kind of mitigate kernel pointers, but we literally have a shared heap that gives you all these pointers. So then they started to basically address this issue. First thing happened, anniversary update, is at GDI level. The GDI shared handle table no longer has pointers to kernel mode GDI objects. Instead, it has indices. So it's not a handle table of indices, and those indices must be translated with a syscall, ntgdi get entry, and then this gives you back a user pointer. So now when GDI components in user space want to touch a GDI object, they go from the object handle to an index. From the index, they do a syscall, and then they get the user pointer. It does slow things down, because before you could go from handle straight to kernel pointer, and then do a delta and get the user pointer. Now there is a syscall, but the GDI team felt, it's worth taking the penalty of a syscall in exchange of not leaking thousands of kernel pointers. So that's great. Unfortunately, there was an inherent bug in Win32K's handle manager that someone found, which was fixed, which still allowed you to leak the address. But then there was a more generic problem as well. So that CV aside, there's a bigger problem. The bigger problem is that GDI objects that come from what's called session space come from the same kernel heap, which is called a session pool, as user session objects. And we did nothing for user objects, which are the window manager objects. We fixed the GDI side, we didn't fix the user side. And since they both come from the same kernel mode heap, and the kernel mode heap obviously uses, like most heaps, an algorithm that says, if you're allocating 37 bytes, I'll find the last free 37 byte slot I had. You basically get reuse issues, or you can come in and allocate a 1,537 byte user object, leak its pointer because user object pointers are still being leaked. So now you have the kernel pointer to a user object, aka window manager object. You then free this user object, and immediately right after you allocate a GDI object of the same size, and you pretty much guarantee your GDI object uses the same slot in the kernel. So you now have implicitly the pointer to the GDI objects as well. So it didn't really matter that they hid where the GDI objects are. The attackers that were creating GDI bitmaps and surfaces can now just create a user object first, free it, and then get the GDI object they want. And this was pretty easy because, for example, an example of a user object is what's called an accelerator table. Accelerator tables are arrays of hotkeys, and you can basically allocate as many hotkeys as you want. Well, by allocating n hotkeys, you're basically allocating a structure of n times 12 bytes. At the GI level, there's bitmaps, for example, and a bitmap, before they introduced type isolation, was the bitmap plus the frame buffer of the bitmap, which followed it, and the frame buffer was basically the height times the length, times the width times the number of bits per pixel. So it was very easy to kind of manipulate and allocate these data structures. And Nicola Economou and a few other researchers gave lots of talks about how to bypass this initial protection that they added. So this really didn't last long, and so in Creators Update, they said, all right, let's go at it harder. And they attacked a bunch of the other data structures that were still leaking kernel pointers. They got rid of the delta, they got rid of the user session, the object leaks as well, and now both tables have either user mode pointers or offsets or indices. So there are no more kernel pointers in the data structures involved in managing the heap, or in the data structures in the TEB or in the PEB. So we think we're good to go. There's just one problem. The heaps themselves have a heap header, and as part of the heap header, one of the things that you have there is the base address of the heap. And since this is a kernel heap, the heap header's base address is the kernel pointer of the heap, at which point you just need to get the user mode pointer of the heap, subtract from the kernel pointer, and you get your delta back. So they kind of left this header behind, which undid the whole point of getting rid of pointers. And there was a second problem as well, which is that although the handle table now had pointers to user mode structures, or offsets to user mode structures, the structures themselves were still basically mapped based on a kernel data structure. So you're still seeing a kernel data structure in a kernel heap. You no longer had a pointer to it. You had a pointer to the user structure, but the user structure is a mapping of the kernel one. And so this still had other pointers inside of it. And so once you got the user pointer to one of the structures and then you read it, then you still had kernel pointers to other stuff. And as soon as you have a kernel pointer to something and the user pointer to that something else, you can compute a delta. And it turns out there's some user objects that, for example, have a header. And in the header, there is a this. Well, the this is the pointer back to the object. So we've kind of moved the kernel pointers one level of dereferencing later. But the fundamental issue is that the heaps are still shared. The heaps still contain kernel pointers. And you just got to go one level deeper and find them anyway. So again, the same set of researchers that broke anniversary update, they released papers on how to break the update. Morton Shank and Nicola and others. So then we take a little bit of a break. And about a year later in Spring Creators Update, they came up with a major, major change to how Win32K works. They basically rewrote, or looks like they rewrote, most of the data structures to no longer have pointers, but actually have offsets instead. Entire data structures got split up. Tag desktop info, for example, has offsets, and now there's a separate structure called tag kernel desktop info, and that one might still have pointers. But anything that still has pointers in it is no longer allocated in the session heap or the desktop heap. There's now a third heap that gets created called the shared heap. So the shared heap is, although the name says shared, no longer shared with kernel mode. Sorry, my bad. The session heap, which was shared with kernel mode, with user mode, becomes kernel only. So these objects go in the session heap like before. And the user mode versions of the objects which have offsets now go in the shared heap, which is the one that's shared. Desktop heap stays shared, but no longer had any pointers in it anyway. Session heap remains with pointers, but becomes kernel only. And shared heap becomes the session heap that is now shared with user space. So now there are 3 heaps, 2 of them mapped in user space that only have offsets. One of them mapped in kernel mode that has pointers. Now, you can imagine the code becomes pretty hard because it must now mean that everywhere inside Win32K.sys, they're doing additions of offsets, additions of offsets, additions of offsets. So kind of cool thing they did is, thanks to C++, they basically use template classes to create template overrides of every single pointer dereference to a structure that's potentially shared with user space, and to basically make the arrow operator do the offset, so that you still think you're basically doing, tag foo arrow p foo, but internally this is an offset now. But it's fine because the overload of this figures out the base address of the heap, adds this as an offset, and then gives you a pointer back. So the code actually is still readable behind probably some header files that are terrible, no one wants to look at, but it made the C++ code not become a complete mess. So obviously this must have been an amount of work that's insane, and the devs of Microsoft that did this, obviously hats off to them for having done all this work. And once this was done, if you then scanned the user space heaps, you found no kernel pointer. In fact, no pointers whatsoever. Everything is now offset based, and job done, mission complete. ASLR is fixed, or at least so it looked. After this work, there wasn't any single presentation or blog post from any of the usual suspects about kind of how to still get kernel pointers. There was, all the names I mentioned, Nicolas, Morton, and Beef, another researcher from the UK. They kind of, I guess it's over now. But it wasn't really over. Now, to understand why it wasn't really over, we have to look at how these new heaps work. And these new heaps use what's called the kernel fixed segment heap. Now, the kernel fixed segment heap is basically an extension of the segment heap. The segment heap is something that they introduced in Windows 10 in user space for UWP applications, aka Metro applications, modern applications, Metro, UAP, the new world of Windows software, Edge, PDF Viewer, etc. Now, huge kudos to Mark Vincent Yason from IBM X-Force. He did the Black Hat 2016, an incredible presentation. I'm actually going to use 2 or 3 of the diagrams he drew, which are really, why redo them? So those are all his. I'll point them out. Really good paper that I'll have at the end in the resource section on kind of how the segment heap works. Now, the segment heap is a completely different beast than the normal NT heap that's been there since 1989. And the segment heap got partially ported into the kernel in 1803 for Win32K.sys. So Win32K.sys actually uses the segment heap. But it doesn't use the normal segment heap, because the normal segment heap supports what's called LFH, low fragmentation heap allocations. The fixed heap, segment heap, which is the one that I implemented in kernel mode, only supports what are called variable sized allocations. So if you do read his paper and his presentation, all the parts where he talks about LFH are not relevant, but all the parts where he talks about variable size allocations are relevant. So it's kind of a simpler implementation of the segment heap that they call the fixed heap. Now, all the data structures are associated with the fixed heap and the variable size allocations, they're all in public symbols. So if you look at the public symbols for NTDLL, you get all this information that you need there automatically. So the fixed heap is basically a subset of that. It's created by RTLP fixed heap create if you pass in create segment heap in user space, in kernel space. So when you pass this in kernel mode, instead of getting the normal LFH segment heap, you get the kernel mode fixed heap. And that's the flag that Win32K uses. Now Win32K passes a second flag called heap create hardened, which then obfuscates some pointers that we're going to be talking about. Now most of the data structures in the fixed heap are the same ones as in Matt's presentation on variable size allocations. The only difference is that with the segment heap, you have an underscore segment heap with the signature of DDDD. With the fixed heap, you have a symbol that's unfortunately is not public. I just called it fixed heap. Could be fixed segment heap. I'm not sure what it's called. And the signature is CCDD, CCDD. So this tells you that you're looking at a fixed heap in the kernel versus a LFH segment heap in user space. But both of those data structures have inside of them a heap VS context, which is the interesting thing we're going to be looking at, the variable size context. And in the case of the fixed heap, it starts at offset 40. So once you know that data structure is at offset 40, everything then in public symbols kind of works out, and you can start looking at it. So one of the things in Matt's presentation is he describes this VS context, right? And so the VS context has these callbacks. Now, so there's an allocate callback, a free callback, a commit callback, and a decommit callback. Now, obviously, these are interesting pointers to an attacker, and so what the segment heap and the fixed heap do is they're going to encode those pointers. And so there is a variable in the kernel called RTL HP heap globals, and in there you have what's called a heap key. So the heap key is basically a 64-bit unique number that's generated every time you boot up the machine. Then all those pointers in this callback context are going to be XORed. You can see here the output from X-rays, where we take the callbacks and we XOR the pointer of the callback with the pointer of the context itself, XORed with the heap key. Or like in the picture here from Matt, function pointer equals function pointer, XOR the key, XOR the address. Now in his slides, you're going to see RTLP heap key, because he talked about the user mode implementation, and that's a global inside of NTDLL. In the kernel, it's going to be this RTLP HP heap globals dot heap key. So slightly different kind of data structure where the key is stored. And obviously the idea is you're not supposed to know what the key is. So this encodes the context, but we can decode it, obviously, if we have the heap key. So if you take the heap key, you can see here that I've got an example in the debugger of an allocate function. And if I take this allocate function, and then I XOR it with the heap key, and then I XOR it with the address of the VS context itself. Now the VS context, interestingly, has a pointer to the beginning of the heap, and you know that a VS context is at offset 40, so if you just add 40 to the beginning of the heap, you know the address of the VS context, XOR those three things together, and obviously you get a pointer, and that pointer is, the allocate function. So if you're in kernel mode and you know all the secrets, obviously, you can get pointers. That's not the interesting part. Obviously, this implies that you're already in kernel mode. I'll talk to you about how you can do this from user space. But from kernel mode, obviously, that's what the kernel itself does to figure out where the function is. So you need a heap key. You need to know the address of the structure itself. And then you XOR those things together, and you get the actual pointer. Now, allocations that you make in a segment heap, whether they're LFH allocations or VS allocations, and again, this is a picture from Matt's presentation as well, have a little header. And the header basically has a cost, a size, a previous size, and an allocated bit. All of these bits together make up a 64-bit value called header bits. And the header bits themselves are then encoded. Now, in his presentation, he talks about using the LFH key, because he was doing a user mode presentation. In our case, it's going to be, again, the heap key. So in kernel mode, we don't use the LFH key, we use the heap key. So we take the heap key, we XOR it with the header bits, and then we XOR it with the address of the block itself, and those become the new header bits. So each allocation has a header, and the header itself is XORed with the key, the address of the header. And we're going to see why this is relevant and useful. So that heap key is used to encode headers. It's also used to encode the context. So we can decode it, of course, if we have all the secrets. So in this example, I took a data structure called the server info, which is allocated here in red at this address. So this is the address of the allocation. Now, the heap header or the chunk header is 10 bytes above it. So basically, we cast it to a chunk header -1 to basically do minus size of header. And this is the address of the header. Obviously, it's just 10 bytes before, well, 16 bytes, aka 10 hex before the allocation. Now, if you actually take the bits in that header, so if you dereference the header bits, which are going to be garbage, and you XOR the garbage with a heap key, and then you XOR it with the address of the header itself, you get back the bits in plain text. And obviously, if you put those bits back, this server info structure, for example, the 6 is the memory cost, 1C3 is what's called the unsafe size, aka this is the size. It says unsafe because it's unsafe to trust, so that's the size. 0 is the previous size, meaning that this was the first allocation, and this one here is the allocated bit, differentiating this from a free block. So free blocks would have allocated equal to 0. This is not a free block, it's an actual pointer, so the bit is set to 1 there. And the sizes here are stored in multiples of heap granularity. The heap granularity is 16 bytes. So if I take the size and I multiply by 16, and I compare it with what's actually being stored at that structure, which is a tag server info, you'll see the size matches up. So that's how you can decode a header. Again, assuming you have all the secrets and you're in kernel mode, which is not what we have in user space until we talk about what the actual issue is. So if you want more information on kind of the segment heap itself, you can read Matt's presentation. But those are the two key things that are relevant here, this XOR cookie that's used and the two situations where it's actually used. Now, what is the actual problem here? So the problem is that if we go back to the data structure heap vs context, one of the things we saw in there is that you get these callbacks. And the callbacks are all XORed. So even if you have access to this data structure in user space, you don't know what to do with those numbers. But in the header of the VS context, there's a field called backend context, backend CTX. That is actually the pointer to the heap. So we've hidden everything away from you, but once again, if you actually go at the beginning of the heap, you'll see a pointer at offset 40 to the beginning of the heap. But now I'm looking at the user mode heap, and now I have a pointer to the kernel mode one. And of course, I can subtract the difference, and now I have the delta. Now, why they didn't catch this is probably because what actually happens is they allocate the heap, and then at offset 1000 in the heap, so this is like the heap header, and at offset 1000, that's what they return back in your user 32, G shared info. It's on the slide as well. Hey, the handle list. So the handle list is basically blah 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 1000. If you look at the PEB, GDI shared handle table, same thing. You get a pointer to a different heap, and this heap has the heap header, and then you get a pointer at offset 1000 in there. So if you just scan from GDI shared handle table to the end, all you'll see is offsets. If you scan the user handle table from the beginning to the end, all you'll see is offsets. But if you're a world-class researcher like me and you think about scanning backwards, then you suddenly find a kernel pointer because the heap header is still mapped. Right? So all these pointers are always blah, 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 0x 1000. I was like, why is it all off by 1000? Let me go see what's at 0000. And of course, at 000 is the heap header, which then has a pointer back to itself, but the kernel pointer. So basically just, scan a page back, and there you go. Now, not only is there a field called backend context, there's a pointer to a bitmap as well, which I didn't show you on the dump here. So there's actually two pointers back to the heap itself. So that leaks the heap, basically where the heap is, and that brings things back where they were before. Now, another thing that kind of did while building a POC for this that was kind of interesting, just a technique I figured I'd share with the world, is if you look at most attacks out there, they go after the GDI handle table. They look after the GDI handle table because it's in the PEB, and because the desktop P pointer is in the TEB. And if you're an attacker and you have an arbitrary read, it's a lot easier to read from the PEB and the TEB because those are easier structures to find. To get the session heap, You need to find user32, and now you need to break ASLR and find where this module got loaded to then find where this export is. But there's actually a kind of complex and clever, if I may say so myself, way you can get this just from the desktop heap. So if you start from the tab, you have the desktop heap information structure, which has a pointer, or today an offset, to the shell window. The shell window has an input method context, and an input method context has the input method editor window, the IME as it's called. The input method editor window then belongs to a class, and so you can find the class for the input method editor class. Now what classes have is they have an owner module, and of course the H module for the class is the pointer to user32. So yes, it's like 15 memory fetches, but boom, you get user32. Once you have that, you can scan the export directory, do a few more fetches, and you can get gshared info. So again, a lot of these heap structures, people assume they only contain pointers that are relevant to GDI or to user, but there's often pointers to modules, to DLLs. There's other interesting, even in user space, things that are leaked here. So anyway, okay, with what I just mentioned, with that simple kind of heap backend context, you're back in RS3 world. So basically, the fact that they randomized the fact that they made everything an offset doesn't matter because you can still compute a delta. But that on its own is not a CVE. You don't get a CVE for basically leaking Win32K.sys data structures, because at the time they didn't consider those in scope for fixing. What they did consider in scope is if you could find a way to leak kernel pointers to kernel drivers or pool allocations or things like that. So if you could leak the module base of a kernel driver, that's something that they would actually fix. So interestingly, by adding this heap, this new fixed heap, they actually made things worse. Because not only did they essentially do nothing, because you could undo it all with this trick, they actually made it even worse because now you could get pointers to Win32K base and Win32K full. The reason for that is that when you create a fixed heap, you can pass in a commit routine. The commit routine gets saved in the header, and then XORed with the heap key. So if you know the heap key, which I haven't talked about how you know that yet, you can get the commit routine. And so here's an example of me getting the commit routine, knowing the heap key, which we'll see what the magic is. And if I XOR the commit routine with the heap key, I get Win32K base user commit shared memory, which of course, if I know the offset of this function, I know where Win32K base is. And so this is for the session heap. If you do this on the desktop heap is owned by Win32K full. So Win32K full owns the desktop heap, and that lets you leak its pointer. Win32K base.sys owns the user heap and the session heap, and that lets you get the other pointer. To make things even worse, though, you could even get NTOS kernel's base address, because that heap vs context that has the allocate, the compare, and the free. If we go back to these routines, these are all XORed pointers that live in NTOS kernel. And so if you do know the heap key, which the whole point is here that there is a way to get it, you can XOR these and now get pointers to NTOS kernel.exe. So the problem is how to get that key, because we know how to get heap vs context, right? Heap vs context is backend context plus 40, so I know where the heap is itself. I know where the allocations within the heap are. I know what the input value, the output value is. XOR is obviously reversible, and so if you can XOR the output with the known secrets, you can get the key back. The problem is we usually have 3 inputs in the XOR, and so I can't get a heap key back unless I know all the inputs. If I go back, for example, to here, well, the input is the commit routine, which I don't know, and the input is the heap key, which I don't know, right? So I have the output, but I need to know one of these values, and the whole point is I don't. I'm trying to leak the commit routine. I don't know it. I don't know the heap key. In the other case, with the context, it's the same. If you go back to how context allocations are XORed, I know the output. I'm trying to get this. I'm also trying to get this, and I know this. So I need to find somewhere where I know the function pointer already. Well, if we go back to how allocations work, remember that allocations basically have the encoded header, and the encoded header is the real header, XORed with the key, XORed with the address of the block. Because of backend context, I can know the address of the block, right? Because I'm told where the heap is, and I just subtract the beginning of the heap from the end of the heap, at the beginning of the kernel heap from the beginning of the user heap, and then add the offset of this block, and I know the kernel pointer of the block itself. The question is, though, how do I know the real header bits? Well, the real header bits, remember, we have the previous size, we have the size, we have the memory cost, and we have a bit that's called allocated. If you pick the first allocated object, you know that unsafe previous size is going to be 0, because it's the first object, so there's nothing before it. It's an allocation, so you know that allocated is 1. And size, well, size is going to be the size of the first object divided by 16. And Win32K always allocates tag desktop info as the first allocation in the desktop heap. And it always allocates tag server info as the first allocation in the session heap. So if you know the size of those structures, which is fixed, divided by 16, you now know unsafe size. The only thing you don't know yet is the memory cost. But memory cost is actually computable as well. On a given OS release, it's pretty much fixed because of how the allocations are done. And even if it wasn't, you can actually compute it by scanning the other data structures, because memory cost is basically how much was committed to make room for this. So for example, on the OS I was playing with, it's always 6 for the first allocation. So I know the memory cost, I know the size, I know the previous size, I know allocated. I know basically all the bits that make up the real header. So this is known, the output is known. You re-XOR this the other way around, and now you get the heap key back. Once you have the heap key, then you can get all the other encoded data where you didn't know what the other secrets were. So basically, this is some pseudocode that I had written when I submitted the bug to Microsoft. I can't demo it because I've been trying to find a VM that's unpatched, and I should have been better prepared, but I didn't. But anyway, here's the output of that POC, where basically I computed where tag desktop info was in kernel mode by using heap context. I cracked the key by creating a fake header. I computed where VS context was by adding 40 to putting this back to 0 and adding 40 essentially. And then boom, by using the XOR key, I found everything that was XORed. Yeah. And so these are all kernel pointers. So I took, for example, the allocate routine here that ends in C80, put in this assembler. Sure enough, that's NT, RTLP, HIP, VX allocate instead of NT. So once you know the offset of this within NT, you know the base address of NT. So this was CV 2018-8637. This was actually fixed and backported and mitigated because now you're leaking base addresses. The other thing, by the way, that's kind of interesting is if you have an arbitrary write, or if you had an arbitrary write in RS4 and RS5, because this was mapped in kernel space and you could find out where it's mapped, obviously once you knew the XOR key, you could use your arbitrary write to overwrite the pointers, and you also now had an execution primitive. Right, so you had a really nice 8-byte primitive for taking control of heap allocations, and as soon as you called free, you can get code execution from that. So it really made the situation worse. Now the fix was really easy. When mapping the section in user space, don't map the first page. Right, so before, like I drawn, they created the whole thing, and then they basically mapped it and gave you offset 1000. Well, now they still give you offset 1000, but they never map this part. There's no reason why in user space you need to know the heap header. All the heap allocations are done in kernel mode. It needs to know the heap header. So the heap header is mapped in kernel. It's not mapped in user space. Because of that, there are no more offsets. There are no more kernel deltas. There are no more pointers. You can scan backwards and forwards. There's nothing there. Very simple fix. Just don't map that, and then the problem's gone. Right? So they backported it to RS4 and RS5. Nothing needed before that because there was no fixed segment heap. And 19H1 shipped without the bug. They fixed it in the preview builds, and so they were able to fix. 1903 doesn't have the vulnerability at all. And so a bunch of MSRC and Win32K.sys obviously helped to get this in there because there was a chance it might have not made it for 19H1, and then you'd have to get a patch for it as well. So thankfully they were able to kind of fix it before they cut the branch back in December. So with that, it's going to get pretty hard now to use Win32K.sys or other the common techniques to leak pointers. And if you look at most of the tutorials and most of the papers you see, they kind of all stop at RS4, and after that is exercise for the reader, because no one's kind of figured out something generic like back in the day. And on top of that, not only did they fix Win32K.sys, but they introduced 2 other really good hardening general mitigations that you might be familiar with. One of them was that when you do IOs, input and output, you provide an input buffer and an output buffer. Now, if your output buffer was actually smaller than the input buffer, because the kernel always allocated the maximum of the 2 structures, you could get back in user space in your bigger output buffer data that was left over from the input buffer that hadn't been zeroed out. And a bunch of drivers had bugs like this where they were returning, saying they were returning more output data than data that had actually written the output buffer. So now the output buffer was leaking contents of the input buffer that had kernel pointers in them. So what they did in RS4 is they now completely zero out this slack space. It's a perfit, it's a penalty cost. Every single ioctal now, which has one buffer bigger than the other, we're going to zero the slack space, but it completely kills that category of bugs where drivers aren't doing the right thing. In RS5, they introduced something called init_all. Init_all is a new compiler option that they now use by default for all kernel mode binaries. So if you compile your own stuff with /kernel, this is enabled even for your own drivers. And this initializes all kernel variables. This basically memsets everything you have on your stack. Obviously, it has a perf penalty, and you can disable it with the decal spec no init_all, which they use on the context structure. But other than the context structure, almost nothing else has this. And if you look in Ghidra or Hexrays at almost any Windows kernel function in RS5 or later, you're going to see like everything being memsetted all the time, because that's what init_all automatically does. So input buffers are being memsetted, so the stack is being memsetted, and who knows, maybe one day even pool allocations might all be memsetted. You know, let's just zero out every time you call malloc in the kernel. Penalty hit, sure, but maybe it's time we address that. And so they're really pushing things to try to avoid leaks of pointers in user space. Another idea that you see implemented on ARM64 that you see in research is the idea of execute-only memory, or XOM. With XOM, you can basically make it so that when that code becomes unreadable. So code is executable but not readable, and this mitigates ASLR violations when you're able to basically fetch or read code bytes. So with all these things on the horizon, getting ASLR pointers in Windows is going to get a lot harder. It's not quite at the same level as Apple, where on iOS, even if you have admin rights, they still consider that a boundary. This is mostly a boundary in Windows only for browsers, only for app containers, or only for low integrity. But they've done a really good job kind of closing that down. And as a result, KASLR bypasses are now in scope for bug bounty, and they'll even get serviced, right? So this bug got serviced, got CVE'd. 5 years ago, if you had a KASLR bug, Microsoft would say, lol, KASLR. And so I think things are getting a lot harder. Now, what's going to happen is obviously third-party drivers are still going to have their own bugs. You're still going to have your bring your own driver, ability there. And obviously, people looking more and more CPU level bugs, right? So Meltdown, Spectre, TSX, cache tagging, lots of CPU capabilities to infer kernel pointers, right? Because CPUs will often share data between the cache or TLB. And so there's probably going to be more and more harder level attacks to leak ASLR information. But those are a lot harder to pull off. They take more time. They're a little bit more noisy. And so, of course, I do think things are getting better. Although, others will say KASLR will never work. There's always going to be one more pointer. And maybe we should stop doing this. But, I think a lot of work went into this, and it's worth kind of celebrating that. So anyway, I'll finish by just saying, again, really, really recommend you read Matt's paper if you're interested more on the heap stuff. All those diagrams, the 2 diagrams I had were from his PDF. And with that being said, I think I'm just on the top of the hour here, so thank you very much, and let me know if there's any questions. Cheers.
Thank you. This was very interesting. So I'm thinking, this sort of a 15-step chain that you discovered, this is something that could have been found by just looking at all such chains, or some such chains, as yeah, you can, obviously a solver would not solve everything, but this seems to be the thing that it could solve, a solver could solve.
Yeah, a solver should be able to solve this, as well as just like scanning the address space for kernel pointers. Like just scan the whole user space address space, and you'd find FFFFF8 something in there. And I think, if you look at Matt Miller's presentation from Black Hat in Israel, I think Microsoft is starting to do more of using SEML and using static solvers and going away from let's just add mitigations to let's actually look at the code for a second, let's analyze it and see if it's secure or not. So yeah, absolutely, and I think they're starting to, if Matt's presentation is to be trusted, they're starting to go in that direction and automatically finding these types of things.
Thank you.
Just a question regarding leaking the EAP key. Essentially, since it's always the same value that's used to XOR different value, have you looked into ways to do just statistic analysis to just recover the EAP key?
I have not because I suck at math, but given that there's so many allocations that all use the same key, I'm sure you could probably derive it in smarter ways. But yeah, I'm not, I'm more of a runtime person, but I'm sure it would work. Okay, all right, well, you can see me after the talk, and thank you very much again.